Hello, my name is Catherine Lee. I'm the marketing manager for the CITARA MCU team. Today we also have Sheetal Lija. She is from our ADC team. She is our product marketing engineer, and we'll talk about some ADC solutions. We also have Petavarus online, and he is our system application engineer, SMTS. So these are the presenters for today. Thanks for joining again. And then let's get started to talk about how to simplify your design and reduce the cost of your data acquisition system with TI AM604 and AM243 products. First of all, let's take a look at our agenda today. First, we will spend around 15 to 20 minutes to talk about how to enable simplified data acquisition system. We will talk about the common applications and CITARA and this ADC complementary solutions, how to evaluate TI solutions. And then we will spend some time to introduce our hero products, including precision ADCs and CITARA processors and microcontrollers. And finally, we will leave around 10 to 15 minutes if you guys have any questions. Okay, let's talk about how to simplify the data acquisition systems. To begin with, I want to talk about the typical use case or the common data acquisition system applications that we are seeing today. On your right side, you can see some typical end equipment that we are seeing today, including medical, like CT scanner, ultrasound, some test and measurement products, and the data concentrator in grid infrastructure application. So, on the left side is the system block diagram. For example, in a CT scanner application, you will have the signal from the scanners. There are all kinds of sensors. You will feed the signal into the high precision ADCs, and these analog signals are usually synchronized or with no latency, or sometimes both. And then you connect your high-speed or high-precision ADCs to FPGA or MCU or MPU, while some high-speed or advanced interface like SPI, ESPI, etc. After the data processing or buffering on the centralized boards, you will connect it to your central controller while some industry Ethernet for further control or processing. So this is some common data acquisition system and applications that we are seeing today. So here's the improvement that we have with TI's newest processors and MCUs. So here's the picture shows the traditional architecture. You have your ADC and connected to your FPGA, and then feed the signal to the optional MCU/MPU. But what we are doing and want to introduce today is to simplify your design, and you can sync the world directly with the TI processors. Basically, on the newest products like AM64 and 243, we have the integrated programmable core. So with this very flexible program core, it enables you to connect it to your TI ADCs with the enhanced interface. And for each MCU or MPU, you can control up to 16 ADCs. So with the new solution, it can indeed help engineers to simplify their design to get rid of the FPGA. And in the meanwhile, it can help you to save your total BOM size, like a BOM cost, and the PCB size. Then we're seeing that let's take a look at the detailed solution about PI, CITARA, and ADC complementary solutions. The purpose of this solution is to address the functionality like multi-channel connection ADC that is implemented on FPGA. The goal here is to directly connect TI ADCs to TI MCU or MPUs. No FPGA is needed. And on the right side, you can see the hardware you will need to get started. First of all, you will need a MCU or MPU evaluation board. So it can either be the AM64 EVMs or AM24 EVMs. And then you will need a ADC adapter board. So it's just like a interface board to connect between EVMs and the ADCs. Then you will get ADC EVMs based on your system needs. Here we provide two examples about ADC 85X8 and ADS 127L11 EVMs. So, for example, for the ADS 8588, you can use these EVMs and sort it on different ADCs based on your system requirements. Or you choose another one with the ADS 127L11 EVMs. So either one will work. The demo today is available at TI Gallery. If you click the link or come to dev.ti.com/gallery, you will check more. You will see more details of this demo. Next page, I'll talk about more details of the available EVMs. So as I mentioned, what you need is very simple, like a MCU EVM, a decking board, and all kinds of ADC that you need. So the previous slide just showed the demos that are available today. But moving forward, we will support more ADCs, and based on your system requirements, you can always find one that works best for your system. Okay, and then let's talk about the evaluation tools a little bit. So as I mentioned, we have a demo available at TI Gallery. So to get started, our goal is to start the evaluation with zero code in your browser. What you need is very simple. All the hardware that I mentioned, the MCU board, the ADC board, and the adapter board, all of these hardware can be orderable at TI.com. And once you get these boards on your desk, you can go to our TI Galleria and launch the demo. For example, right here, we are using ADS 85X8 demo as an example. After connecting all the boards and launch it at TI Galleria, you can capture and view the ADC samples in real time. So on the right side, you can see a few pictures, which just show you the details of the evaluation tools. So the first picture is a simplified block diagram about the connection. You will have your SITAR EVMs connected that via the adapter board to connect to your ADC EVMs. And the green picture is just the real hardware of the system connection. And the picture below just shows the ADC samples. We have some screenshots of the real demos. What's the trigger signal and what kind of ADC signal that we are seeing in the SITAR EVMs. So our goal here is to start the evaluation with the zero code. You just need the hardware. You need to launch the demo at TI Gallery and see the real ADC sample results. We have already programming all the codes and the demos on the TI Galleria. So you don't need to do any programming, but can get the evaluation started now. If you finalized the details of the ADCs and all the details, and if you want to get started with the development, you can start the development code with our MCU+ SDK. The next page is about MCU+ SDK configuration. So we are assuming you already finished the evaluation and figured out the ADC, which ADC, what kind of performance you will need. And when you come to the MCU+ SDK, this is just like a user interface, for example. What you will need is very simple, just to select the ADC that you need in your system. And then you can just start the standard programming and based on your system needs. If you are interested in this solution, like the additional ADC attached resources, we indeed have the real demo with the video record at TI.com training and video series today. So if you want to watch the video and check more details, you can just go ahead to scan the QR code on the screen. And the QR code will help to direct you to the TI training and the video page, which will show you the live demo about direct connected to ADC with CETERA, TI CETERA MCU and MPU. And in that page, you can check more details of how of the system configuration, of the hardware connection, and how we get started. Okay, then in the following few minutes, I will switch it to Shita. She will help to talk about some high precision ADC solutions from TI.
Thank you, Catherine. Hello, everyone. I'm Sheetal Lidar. I'm the product marketing engineer from Precision ADC at TI. As we plan to build this library of supportive ADCs to interface with CETERA, I would like to take this opportunity to present two ADCs from our portfolio that already has the demo code released on TI.com. With these two ADCs, you can technically initiate your development immediately. The first one is our newest flagship device, the ADS127L11, which is released on TI.com. And this is our wideband Delta Sigma ADC with integrated input buffers as well as the VREF buffers, as you can see in the block diagram below. This buffers technically help with the front-end design and help directly interfacing these ADCs with the sensor interface. As you can see in the block diagram, this ADC offers two filter modes, the wideband filter mode and the low latency filter mode. The wideband filter mode enables the designer to have input bandwidth of 165 kilohertz. This filter mode supports maximum sample rate of 400 kSPS. In the low latency filter mode, this ADC can support maximum sample rate of 1 MSPS. In this mode, the one can get the fast step response as close to 4.3 microseconds. The filter modes, the power needed by this ADCs is actually scalable to what filter mode the user selects. This is a flagship device, as I mentioned, based off the new process technology from TI, which enables us to release this product in the smallest size, which is a 3x3 QFN package, which is the industry's smallest with respect to this class of ADC, and it offers half power and much more wider bandwidth when we compare to a nearby competition. As you can see in the next slide, this ADCs here is the ADC highlighting its feature set. It offers the best-in-class AC and AC precision and DC accuracy, as shown in the graph down below. I did mention about the smallest size this ADC is being built on, and the daisy chain option. So if there are multiple channels needed, you could technically daisy chain multiple ADCs up to 16 and more. And we do have a nice app note on what are the key care-abouts of daisy chaining this ADC in the simultaneous sampling mode. One thing I want to go back to the prior slides to talk about the different applications this ADC could be used. Catherine did mention about a variety of data acquisition system, but I would like to highlight this particular ADC. We have seen good traction in condition monitoring type of application, a lot of pressure and ultrasonic sensors, and any data acquisition that needs much low power. The second ADC, to the next slide, that I would like to highlight is actually a family of devices, the ADS85XX family. As you can see in the table, this is different type of ADCs offering resolution from 14 to 18-bit, and this is a multi-channel ADCs, 4-channel, 6-channel, and 8-channel are all listed, supporting different sample rate from 200 kSPS to 500 kSPS. This particular ADC is actually integrated with, as you can see in the front end, a lot of front end is already designed in, and you could actually use this ADC to directly interface with the sensor. It does offer very high input impedance, and user can actually program. It is a programmable input range, either plus or minus 10 volts or plus or minus 5 volts, depending on the design needs. You could use this ADCs in interface with the Sitara. So these are the two ADCs, again, similar type of, slightly different applications, as you can see, test and measurement, battery test, and protection relay. So these are the two ADC family that we have already developed the code to interface with Sitara. As we plan to increase our library, we plan to increase a different variety of other ADCs to support this interface. So again, two examples from Precision ADC team, but stay tuned as we release further more ADCs to interface with this port.
Okay, thanks, Ishita. Okay, then let's spend some time to talk about Sitara processors and microcontroller solutions as well. To begin with, I want to start with the AM6442, which is a Cortex-A53-based processors. So this page, you can see the AM64 block diagram. Basically, this device will offer up to 2 Cortex-A53, up to 1 GHz, which can offer up to 6K DMIPS performance. And besides the A53, we also have the real-time cores for the real-time control application. We offer up to 4 R5F, up to 800 MHz. So for these R5F, you can also get up to 6.4K DMIPS. Besides that, you also have we also offer a Cortex M4 on the device. So this Cortex M4 is mainly for safety monitoring. So if you have any safety-related application, we indeed offer the safety like MCU to do the safety monitoring. On the device, we also offer up to 2 MB on-chip SRAM with ECC. This should be big enough for any application required on-chip SRAM. We also offer another programmable real-time unit industry communication subsystem. So with these 2 communication subsystems, you can use this subsystem to do industry Ethernet. For example, like TSN, EtherCAT, Profinet, Ethernet IP, L-Link, etc. Or you can use the programmable real-time control unit to do some motor control, like sigma delta filters, and handle some absolute encoder interface, like a hyperface DSL in data 2.2 to Magawa, etc. We also offer the security HASM on the device. So if there is any security critical application, we should be able to support that as well. And then let's talk about some peripherals on the device. We indeed offer some high-speed interface, including 2-port gigabit Ethernet switch with 1588. We also have one PCIe generation 2 to enable some high-speed communication. USB 3.1 or 2.0 is also available on the device. From the memory side, we also offer the DDR interface. We can support a 16-bit DDR4 or LPDDR4 with ECC, GPMC, QSPI, and these standard memory interface are also available. We also have some other low latency interface like FSI and some other general SPI, general connectivity and I/O like SPI, GPIO, ECAP, EQEP, etc. So these should be good to do any general industry connectivity. So today, AM6442 is available at TI.com. And we offer a big package, 17 by 17 with 0.8 ball pitch. Next page is about the AM64 family. Besides the AM6442, we indeed have a few different variants with multiple pin-to-pin compatible solution. So with this page, you can say we have a few different options with different numbers of the ARM Cortex-A53 cores, ARM R5F cores, some industry networking option, and integrated stack options. So in short, the goal for the AM64 family is to offer you a scalable family options. We can span the broad range of the performance levels to enable pin-compatible solutions. And it can help to maintain real-time performance, even with Linux servers running simultaneously. From the industry side, we support from -40 to 105 degrees C, covering some typical and general industry temperature requirements. Yeah, we also support industry communication solutions, including Profinet, EtherCAT, Ethernet IP, and IO-Link. The customer can get the silicon and pre-integrated stack from TI directly. We also offer up to 100K power on hours and at 105 degrees C. Functional safety is also supported. As I mentioned, we have a Cortex-M4 on the device for safety monitoring. So we can support up to L2 for functional safety. If you don't need A53 for the Linux, we also offer some pin-compatible solution. We have AM243 available. So this device, the total power consumption is less than 1 watt. In next page, I'm going to talk about AM243 a little bit. AM243 and 64 are the scalable family with each other. As I mentioned, if you only need a real-time control core like the Cortex R5F, and you don't need the A53 for Linux, you can go and take a look of the AM243 family. So the difference between AM64 and 243 is AM64 has both R5F and A53, while the AM243 only offers the R5F on the device. So we're seeing that we need to offer the pin-compatible solutions. All the devices are in 17x17 and they are pin-compatible. And in the meanwhile, if you have any space-constrained application and need a smaller package for AM243, we indeed offer a smaller package, 11x11 with 0.5 ball pitch. And similarly, security boot is also available on AM243. So AM64's target power consumption is less than 2 watts. If you only run R5F, the target power consumption should be less than 1 watt. The next page is about the AM243 system block diagram. So similarly with the previous one that I showed about AM64, AM243 have similar Cortex R5F up to 800 megahertz on-chip SRAM with 2 megabytes, programmable real-time unit industry communication subsystem to enable industry Ethernet or the motor control protocols. We also have M4 for the safety monitoring, security enabled, CDR enabled. All the interface will be very similar. So the major difference between 64 and 243 is just the A53, whether we have that. And secondly is the package. For AM243, we indeed offer another smaller package for a space-constrained application. But either way, you can get started with either device based on your system application. I think either one should be a good start point. To get started with TI AM64 and the 243, you can go ahead to go to our TI.com and search AM6442 or AM2434. So these devices are fully available online today. You can find the product folder with the data sheets, evaluation board, technical reference manual, and some application resource available online. Or you can also go to our TI software development tool, start development, debug, and analyze the code in the cloud. You can just scan the QR code to get started. On the TI development tool, we indeed offer a very rich full tools for you on the cloud side, including Resource Explorer, TI Gallery, CCS Cloud, Edge AI Cloud, System Configuration, UniFlash, and GUI Composer. So we indeed offer very enhanced development tools in the cloud. Just to scan the QR code and get started. Okay, I think these are all the introduction we want to have today, and we will stay online for a few minutes in case there is any question online.
Okay, yeah. Hey, thanks, Catherine. It's Pekka Varis, and I'll kind of moderate the questions from here. So, yes, so there's and feel free to ask other questions either through the chat window or the Q&A window. I've tried to look at both here, but okay. So just as a general, so all these part numbers are released part numbers, so they have data sheets. So for the details on the for example the ADS 127L11, the details of it are in the data sheet. Okay, so that's kind of covering one of the questions. Then we do another question. Okay, so yeah, so question on do we require an external debugger JTAG pod? No, we do not require an external JTAG pod. So the evaluation modules, the EVM, it has an onboard debugger. So essentially a USB 2 cable disconnected to your machine, and then in the simplest the browser approach, the zero code approach, there's actually underneath in the browser it's using a JTAG to load the code and so on, but that's transparent to you as a user. So and then if you go farther, even then you do not need a separate JTAG pod. You can use the onboard debugger. Now we do allow you to use, if you prefer to use like a more advanced, let's say a Lauterbach debugger and so on, those are supported as well, but not required. Okay, then there's a couple of questions kind of around the microcontroller core, MCU core, and the processor core, or so this. So the current, so in this family of devices, we have like Catherine was showing, we have some of the devices have Cortex A53 cores, which typically would run Linux, so a high-level operating system, and require DDR. Then we have one or more R5 cores. In the maximum case, 4 R5 cores. Those would be running typically a FreeRTOS. The software development kit we call it the MCU Plus, or that's a FreeRTOS with the drivers. So these ADC examples that we have, they're basically based on the R5 core, so they're utilizing the R5 core. Then we have an IPC messaging mechanism between the cores, also able to talk to Linux. So the kind of the real-time loop to get the samples into the device is controlled. The example drivers are all on the R5 core, so they will run on both the AN64 Linux-capable processor and then the Citara MCU. We are looking at doing a native Linux driver as well, but of course the real timeliness is going to be different. The R5 cores are in the microsecond range of guarantees and so on, while Linux is going to be in the tens of microseconds or more like 100 microseconds. Okay, let me check another question here. Let me see. Okay, let me take. So there's a question on the ADC max sample speed. So the ADCs the examples we support, currently we're in the one mega sample range. So these are precision ADCs. The capability of solution does go up to maybe high-speed ADCs at the 80, so 80, or maybe even 100 megasamples per second. We don't have, in the current software SDK, we don't have examples for those. We have some internal demos, and we're looking at expanding there towards a higher speed. But these are like the ADX127L11 is a 24-bit ADC, so it's a high precision at a megasample range. Okay, then let's see, I have another question here. Let me see which one there's a distributor. So where do you get these? So these are all available from TI.com. So there's a question on our availability through distributors. Actually, I don't know, Catherine.
Help to answer that. Yes. So to get started, if you are interested in earning TI solutions, there are a few options. One is go to TI.com. So at TI.com, at TI Store, we indeed offer all the like a hardware unit, including both silicon and evaluation boards. So you can just go ahead to have a MyTI user registered and go ahead to order the samples or EVMs online directly. And at TI.com, we indeed have some stock for all the boards and silicons. And if you want to work with like some local vendors, like a distributor, Arrow is TI's distributor channel today. So you can go ahead to reach out to your local Arrow DSP for further technical or like business support.
Okay. Yep. Thanks, Catherine. So, and then let me see. I had another question here. So there was I kind of mentioned that the details of the ADC are in the data sheet. So there's a specific question on the low latency filter that was mentioned in that. So I think that it's a Sync 4, Sync 3, and Sync 1 filter, and the details are again in the data sheet. So that specific ADC is kind of intended for two use cases. Looking at AC signals, it will be the white band, and looking at DC signals, that will be the low latency filter. But the kind of the exact details of the filter are in the data sheet. Then let's see, I have a little bit of a question on maybe the couple of questions somewhat close to each other on the A53 MCU MPU area. So let me try to answer. I mean, I partly answered, like, primarily the AM64 makes sense if you want to do if you want to run a high-level OS. So if you want to run Linux in your system, then if you that would drive the usage of the processor. Now it does have some fairly powerful capability on like an FFT and some kind of heavy compute side. It's more powerful than the R5 core, but the primary use case I would say is the high-level OS. If you don't need a high-level OS, then the 243, which is the Cortex-R cores only, is most likely sufficient for your for the use case. Okay, I think that's. I think I covered the questions that I saw on chat. If there's further questions, feel free to type them in. All right.
Okay, if no further questions, I think that's all today. That's all for today. Thanks everyone for joining. We will have a video record and at TI training session. If you guys are missing the training, some sessions, or want to forward to any friends or and colleagues for this study. And yeah, we will please stay tuned about the video record and also for more newly released demos and the development tools for the ADC attach. Okay.
All right. Thanks everyone.
Thanks everyone.